Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, let's start today's lecture. And first of all, still welcome to today's lecture. And I have some announcements. First is about assignment, and obviously assignment will be due tomorrow at 11 a.m. at the administrative office. So basically no late submission and please take everything into the consideration when you submit your assignment, including traffic and also parking at ANU. So there is no excuse for late submission for the assignment. So any questions about assignment? Okay. So let's just continue the previous topic. So our previous topic is about Poisson log linear regression model, a new type of regression model. And the Poisson log linear regression model is used to model the number of real events, if you still remember. And in our specific case, we consider the number of the to model the number of the car accidents. So our response variable is the number of the car accident. So this is our response variable, and when we use R to fit the model, we usually just still use the GLM function, and then we put the response variable and also the explanatory variable. Here, the explanatory variable is the number of the traffic lights in each county. And after we put the response variable and also the explanatory variable, and we are going to set our model. So here we consider the Poisson log linear regression model. So the family is Poisson. So what's Poisson mean? Poisson just means one of the assumption for the Poisson log linear regression model. So that is the response variable Z follows the Poisson distribution. And then we need to specify the link, or link equals to log, so which is different from what we have learned in this course. So earlier we have the binary and binomial and also multi-category response regression model. We all have link function logic, but here we have a change here. We consider the link function as the log link. So what's the link function mean? So here we just mean that it's actually our, so if you still remember, our assumption 1 is the Poisson distribution assumption, and our assumption 2 is the generalized linearity assumption, which is mu z given x and we consider the transformation of mu, and here we consider the log transformation, so which is the log link function, just equals to beta 0 plus beta 1 x. So this is the our model, the second assumption. And also we have the third assumption, which is the independence assumption. So here we only have 3 assumptions. And by specifying this GLM function, and the next step is just to use the summary output to have a look at the result. And I think everything keeps very similar. I think if you can understand the binary logistic regression, binomial logistic regression, I do not think that's hard for you to understand this table. But I still need to, I think I have already explained some of the table, but in today's lecture, I still need to emphasize the non-residual and also the non-deviance and also the residual deviance. Yeah, even if I have already, I think, repeated these 2 figures for a lot of times in this course. And also, these 2 figures are questioned, I think, in your assignment too. So basically, the non-deviance is the deviance of the model with the intercept only. And the residual deviance is exactly the deviance of the model we fit, which is we model the number of the car accidents as a Poisson distribution, and the mean of the Poisson distribution is a function of the number of lights. So that's our model. And by using this tool, we can construct the drop-in deviance test to test the overall significance. And how to do that, so we can try to use R to help us to do that. And in this case, because our model here is log mu z given x equals to beta 0 plus beta 1 x. So this is our model. So that means because we only have actually 2 coefficients, and 1 coefficient here, beta 1 corresponds to the coefficient of the explanatory variable. Because we only have 1 explanatory variable, so testing beta 1 equals to 0 is also testing of overall significance in this case, because we only have 1 variable. So this is really special. And in order to perform this drop-in deviance chi-square test, and I do not think that's hard, and basically the idea is similar to the binary or binomial logistic regression model. So in order to perform it, we need to consider the reduced model and also the full model. So here the reduced model is the model with the intercept only, because when beta 1 equal to 0, so the model is reduced to log mu z given x equals to beta 0, so which is the model with the intercept only. And what you need to do here is just to input the response variable and also the explanatory variable, which is the intercept, and then fit the model and obtain the reduced model. And for the drop-in deviance test, the idea is just to compare the reduced model and also the full model, and then look at the difference of these 2 models to construct the drop-in deviance test statistic. So here we have these deviances of these 2 models. So firstly, we have the deviance of the reduced model. So this is the deviance of the reduced model. So we have the reduced model, I think, by regressing the number of car accidents on the intercept. So this is the deviance of the reduced model. And also we have the deviance of the full model. So the deviance of the full model is actually the model we fit here. So I think maybe I can write down what's the reduced model and what's the full model. So the reduced model here can be simply expressed in this way. And this is the deviance of the full model with the one explanatory variable. And if you compare these two figures, 75 and 51, you can also find these two figures in the summary output. So that means you can actually use these two figures to perform this overall significance test. And the next step is just to obtain the difference. So the difference here is our test statistic. And by using the test statistic, we can compute the p-value. So here, the p-value here is smaller than 0.05. So that means we should reject the null hypothesis. So that means x, so here our x is the number of the traffic lights in each county is actually useful in explaining the number of the car accidents. And also because we only test one coefficient and we have the number of the degree of freedom. So this one is actually the number of the degree of freedom. So this is how to perform this dropping deviance chi-square test. And I think maybe it's the last time I repeat this test. So any questions for dropping deviance test?
So what's the difference with the chi-square test and the z-test?
Okay. Thank you so much for this discussion. So the student asked about what's the difference between the chi-square test and also the z-test. Very good question. So let's try to review some part in, I think, in topic 11. So if you really do not remember how to perform the hypothesis testing and also the confidence interval, so my suggestion is just to try to review topic 11, because topic 11 is actually for all the generalized linear models, including the Poisson log linear regression model. And in this topic, we mentioned about the z-test and also the dropping deviance chi-square test. So the difference between this test here is that for z-test can only be used to test only one coefficient. So you can see it from the hypothesis, non-hypothesis. But the dropping deviance test here can be used to test several coefficients. Because it can be used to test several coefficients, so that means it has a lot of situations, and we give three special cases. So the first case is just to test a subset of coefficients. So I have already shown you earlier. And the second case is just to use to test the overall significance. So that means we want to test all the coefficients except for the intercept. And this is the second case. And also we have the third case is used to test a single coefficient. And when we have this third case, when we try to use the chi-square test to test a single coefficient, so we can find that even though we have different test statistic and also a little bit different p-value, very similar p-value, but we should have exactly the same result as the z-test because they test basically the same thing, which is only one coefficient. So that's a brief review. And then let's go back to our case. So in our case, because we consider only one explanatory variable, this is our only one and only explanatory variable x, which is the number of the traffic lights. So in this case, if we want to test the beta 1 equal to 0, so that is only one coefficient, right? If we want to test only one coefficient, we can look at the z-test. So for the z-test, the result is it is in the summary output, and we can see the p-value is smaller than 0.05, and in that case, we can reject the null hypothesis. So that's the z-test. And because dropping deviance test can be used to test, can also be used to test only one coefficient. So here, we basically consider another test you can consider in this way to test the same null hypothesis. And we can also find that even though we have a slightly different p-value, but we basically have the same conclusion. And because in this example it's really special, we only have one explanatory variable, so you will find that the z-test for beta 1 and also the chi-square test for overall significance and also the chi-square test for one coefficient, they are all the same. Because in this case, we really have this very special situation with only one explanatory variable. But if we have two explanatory variables, this testing of overall significance, so for instance, so if we have mu z given x log equals to beta 0 plus beta 1 x1 plus beta 2 x2, and in this case, we will have the testing of overall significance. Becomes the null hypothesis is beta 1 equal to beta 2 equal to 0, and the alternative hypothesis is otherwise, basically the opposite of the null hypothesis. So in this case, we are going to have two coefficients instead of the only one coefficient in this very special case. So basically, we have a very special case. So we have the z-test, chi-square test for testing of overall significance, and also the chi-square test to test only one coefficient. They are all the same because of this very special situation. Any more questions? Yeah, since we are not going to have a review, lecture in this course, so if you have any questions, you can ask me, and during my lectures, I will try my best to help you review. Okay, and the next is just to have a look at what's the fitted value, what's the prediction by using the Poisson log linear regression model. So if you still remember, for Poisson log linear regression model, we have explanatory variable and also we have Poisson count. So what's Poisson count? So Poisson count basically is the number of the real events. So that you can consider that as some review. The number of real events. The number of real events. So in this case, the Poisson count Z, which is our response, is modeled by the Poisson distribution. And if you still remember, if Z follows the Poisson distribution with the mean parameter mu, and then we can directly obtain this result that the mean of Z just equals to this parameter mu. So that's the conclusion from the Poisson distribution. So that's actually some property of Poisson distribution. And by using this property, if you still remember, so this is from the Poisson distribution assumption. And if we combine this assumption to our generalized linearity assumption, which is log mu equals to the beta 0 plus beta 1 x1 plus so on and so forth plus beta 2 beta k xk. So this is our model. If we combine these two models, we can find that the mean of response mu z given x just equals to the exponential of beta 1 plus beta 0 plus beta 1 x1 plus so on and so forth plus beta k xk. So this is the another form, an equivalent form of the generalized linearity. So by using this form, we can consider the fitted value as the estimated mean of response. So the fitted value is the estimated mean of response by plugging in the maximum likelihood estimation results. So still the similar idea by plugging in the estimation. And a little bit, I think, review or comparison. So you can compare it to the, so I think maybe we should write it here. So if we look at the fitted value, for multiple linear regression model, what's the multiple linear regression model? That's mu y given y equals to y given x equals to beta 0 plus beta 1 x1 plus so on and so forth plus beta k xk. So you can find that basically the difference here is that the Poisson log linear regression model is the exponential of the linear combination for the mean of response. But for the multiple linear regression model, it's strictly the linear combination. So because of this result, and if you still remember the fitted value in multiple linear regression, so the fitted value in multiple linear regression is also equal to the estimated mean of response. Right? We use the estimated mean of response to consider it as the fitted value of the mean of the response variable. So similarly, we also use the estimated mean of response as the fitted value for the response variable z. So the idea are consistent. So we have a slightly different model, but the idea for the fitted value is the same. And when we talk about the fitted value, we usually mean that x is from the training data set. But if we consider some new x from the test data set or from some new data set, we actually talk about prediction. And I think you have already done something about how to use the test data set X to predict the response variable in your assignment 2. And let's just look at how to obtain the fitted value. So basically, when we talk about the fitted value, we mean we consider the training data set, which is the data set we use to fit the model. So which is usually the data set we use to fit the model. And how to use this data set to obtain the fitted value in R. And in this plot, firstly, I plot the number of car accidents versus the number of traffic lights. So the y-axis is the number of the accidents, and the x-axis is the number of the traffic lights. And secondly, I just try to use our Poisson model to obtain the fitted value. So this is the fitted value. So if we have the x as the number of the traffic lights, and then this is actually the fitted value z hat, which equals to mu hat z given x. That's our estimated mean of response by plugging in the estimation, maximum likelihood estimation. And here we only have one explanatory variable. And here, how to obtain this fitted value? So what we need to do here is just to use the GLM function output and $ the fitted value, and then we can obtain this fitted value. So if you have a look at this fitted value, so this fitted value is represented by the solid line, and you can find that it's exactly the exponential of x. So it's an exponential function of x. From the plot, we can see it very clearly. And that's how we obtain the fitted value in R. And let's look at how we obtain the prediction in R. So nothing so different. We still use this predict function. So here, let's consider that in some specific county, we have the number of the traffic lights equals to 31. So that's predict the number of the car accidents in the past year for this county. So what we need to do here is just to construct a new data frame for our new data set, 31. And you need to make sure that the name here, I think maybe it's also the last time for me to talk about this predict function again. And you need to make sure that the number, the name here, number of lights, should be the same as the name in the summary output, the number of lights. Otherwise, you will have, and R will report error, I think. And by doing that, we can use this new data frame here to predict the number of the car accidents in this county. And what we need to do here is just to input the GLM output and also this new data set. And we need to specify type equals to response because we want to predict response. And in this case, we are going to have this prediction, which is actually the prediction. So what's the prediction? That's Z. Also, we also use Z hat. But this Z hat equals to the new hat, which is Y given X new by using the new data, and which equals to the exponential of beta 0 hat plus beta 1 hat X new. So if we have the new data, we usually call it prediction. We do not call it fitted value. So basically, the only difference is the name. And here, because Z is actually a number, right? So that means we need to have an integer to predict Z. So in order to do that, so roughly speaking, we can use this round function. So basically round this figure to 0 decimal. And in this case, we are going to have 2. And in this case, we can say that roughly speaking, we have this prediction of the number of the traffic lights, which is 2 for this very specific county. So that's how to use R to obtain the prediction. Any questions? Sorry, could you wait to me for a while? Because of the echo, and also it's really far away.
What if we don't specify the number of lights? What if we just say data frame number of lights and that's it? Just length of X.
Okay, so your question here is that we do not specify X new, we just put data.frame exactly in the predict function. Is that? I think you can do that.
Yeah, but what will happen? Will the predict function be able to actually predict something?
We can have a try in R now. Okay, we can have a try. So what's your question?
My question is that can we use this predict function to get the probability of that X to
I think that's a very good question. So if you want to obtain the probability instead of the response variable, so I think here we have two questions. So I will try to show that in R. And when I do it, so when I do it, I will repeat those questions such that those questions can be recorded. Okay, so let's just have a look at the R. And firstly, I think you need to do here is just to open R. I think I have already saved R here. And the first, okay, so I may also need to save the data set, otherwise I cannot do anything. So the data set is here. Yeah. And the first thing you need to do here is just to change the working directory. I think that's the working directory, right? Yeah. And then, so firstly, read the data in and fit the regression, and then we have our prediction. So let's just have a look. Yes, so this is our prediction, which is equal to 2. So I think the first question here is that how about we do not specify x new, we just use the data frame directly in the predict function. And so let's just have a try. So if you put this here, data.frame here, and then you can also run R. And you can see that you can exactly obtain the same thing. So you, if you do not want to, you can actually put data.frame, this whole function, into the predict function. So do I answer the first question? And the second question here is that if we want to predict the probability, but we do not want to predict the response variable, so what we are going to do. And I'm not sure about this question, but we can have a try, because if you still remember the topic 14 or topic 12, multi-category response regression, we can actually use it to predict probability. So maybe we can have a try, but I cannot guarantee it will work. So I think if you really work on your assignment very hard, you will find that I think the trick for R here is basically try and error for me. So basically what you need to do here is that if you have some ideas, you can have a look and have a try, and to see whether or not R will work. If it will work, so I think it's fine, but if it will not work, so what you need to do here is just to search Google. So I really do not have any better suggestions. Yeah, so here we do not have the probability, so that means we cannot use this probability to obtain the probability of Z. And also, I think in our topic 11, maybe topic 10, we also provide how to predict the probability of the binary response. So let me have a look. So in that case, that also use response. So basically here, we cannot use the predict function. So the second question from the student here is that the student want to get the probability of the response variable Z instead of the response variable. So here, in order to do that, we cannot use the predict function. So that's my first answer. You cannot use the response function, this predict function, by using the type equal to response. And you cannot just replace it by using probability and then obtain the probability of Z. So that's my first answer. And my second answer here is that we need to, if we are really interested in the probability, we need to use the model to help us to compute the probability. And so let's go back to our topic. So if you still remember our model, so our model has 3 assumptions. The first assumption is the Poisson distribution, and the second assumption is the generalized linearity assumption, and the third is the independent assumption. So here, I think the first assumption specifies the probability, right? So here we have the probability of Z given small z. And in this case, so what you need to do here is just to firstly use the second assumption to obtain the estimated mean of response. So maybe I can just add a page or something such that you can know it more clearly and how to obtain the estimated probability. can add a page. Yeah, I think that is really a good question, and that's in my old lecture notes, but not in this version. So how to obtain the estimated probability of z given some lowercase z. And the step 1 here is to obtain the estimated mean of response. So that is mu hat z given x equals to beta 0 hat plus beta 1 hat x1 plus so on and so forth plus beta k xk, and then define it as mu hat. So that's the first step to obtain the estimated mean of response. To obtain the estimated mean of response. And the second step here is just to obtain this estimated probability. And here, we can call this probability, maybe we can call it P lowercase z hat. And by using so this is from the generalized linearity assumption. The step 1 here is from the generalized linearity. And this step 2 is from the Poisson distribution assumption. So it equals to the Poisson probability, so which is the exponential of minus mu hat times mu hat to the power z, and then z times z minus 1 and z minus 2 times so on and so forth times 1. So that's how we obtain the estimated probability for some response z given the explanatory variable. So we need to estimated probability of z given x1 to xk. So that's the steps. So in R, we can try to implement this idea. So how to do that? So how to do that? And firstly, we can obtain the mean of response. So here we can actually obtain the estimated mean of response. We can call it hat mu, just equals to this predict. So that's our first step to obtain the estimated probability. And the second step of the estimated mean of response, sorry. And the second step is just to use the formula to obtain our estimated probability. And I think in R we should have the probability of Poisson distribution. I think it's PPOS IS. So we can have a try. Yeah, you can see here we can compute the probability here. We can compute the probability of so the DPOIS here, and I think it's the density, and here this should be the probability, and this should be the quantile, and this is the random variable. And I think in the Bootstrap topic, we are going to use the RPOIS to generate the Poisson random variable. But here, in order to compute the probability, we need to do in this way. And then here we need to input lambda. And here I think in this case we obtain the probability of I think it should be smaller than Q, but we should have a look at it. So firstly, we need to specify lambda. So lambda is actually our mu here because it's actually mean. And let's just look at the probability function. So what's the probability function gives? I think the probability gives us the probability that smaller or equal to Q, so we can have a try of it. Yeah, we can have a try here in R. So PPOS, and we need to input the probability, and so maybe let's just specify small z, the lowercase z equals to 0, and we want to get the probability that smaller or equal to 0. So that's z, and the next argument is actually our estimated mean of response. And in this case, we get this probability if z is smaller or equal to 0. And also we can have a try maybe -1, and I think we should have 0. Yeah. And let's also try maybe 1, smaller or equal to 1. So you will have this probability smaller or equal to 1. So you need to be very careful here when you want to use R to obtain the probability. I think usually we have this probability that smaller or equal to 1 instead of the probability that z equals to 1. So if you want to get the probability that z equals to 1, so I think you may need to use the probability that y equals to 1 minus the probability of z equals to 0. And this is the probability that z equals to 1. So I think this is a little bit beyond the scope of this course. So I think you just need to know that actually we can compute the estimated probability in this case by using this PPOS function, but you need to read the instruction, read the help in R to understand the PPOS function. And also I think you need to review the lecture notes in 1008 or 7055 in order to understand how to compute the probability in Poisson distribution. But obviously it's not required in this course, but what I need to tell you here is that if we can compute the mean of response, to compute the estimated mean of response, we can use this mean of response hat mu to compute all the probabilities. Any more questions? Okay, so let's try to continue. I think I talk about something a little bit beyond the scope of this course, but I think it's fine. So I think earlier we can compute the estimated mean of response z hat, and if we have this z hat, we can use this z hat, or we can call it mu hat, to compute the estimated probability. So this is the estimated probability of z. Yeah. So that's the. So I need to write it again. Estimated probability of z equals to the lowercase z, and given values of x. And also we can use the three diagnostic tools to help us to perform the diagnostics of the Poisson log linear regression model. And before we talk about that, firstly, I need to answer the questions from the discussion forum. So the students basically on the discussion forum have already read the lecture notes, and they have some questions about the diagnostics. So we can firstly, let's just look at those questions. So basically that's the motivations, and then we can just look at the details of the model diagnostics, these three diagnostic tools. So in this question, the student asked about how to basically to diagnose these three assumptions: the Poisson distribution, generalized linearity, and also the independence assumption. And the student suggests to use this plot which equals to 1, so which is something I haven't talked about, but I will briefly mention, I think, later in the course. So can we use that to check these three assumptions? So that's the first question. And the second question here is that, so if we can use this plot to check the linearity assumption, and how can we check the independence assumption? And how can we check the Poisson distribution assumption? So my answer is that I'm going to answer this question now. So let's just look at, so based on this motivation from the student, let's look at how to check these three assumptions of the Poisson log linear regression model. So firstly, let's just look at this log response versus explanatory variable plot. And in this plot, so basically you can just compare this plot to the multiple linear regression model, the response versus the explanatory variable plot in multiple linear regression model. But here we consider the log response instead of the response versus the explanatory variable plot. So here, this idea is from the generalized linearity. Because this idea is from the generalized linearity, so this plot, I think, is mainly used to check the generalized linearity. So this plot is mainly used to check our assumption 2, which is the generalized linearity. So what's the generalized linearity? So the assumption is here. So that means the logarithm of the mean of response fall on a straight line function of the explanatory variable. And here, in order to check this, so we need to consider something to approximate the mean of response, right? Because mu is unknown in this assumption. So the mean of response is unknown. So that means mu is unknown in this assumption. So in this in this case, what we need to do here is just to find some way to approximate this mu in order to help us check this assumption. So what we do here is just to use the z to approximate mu given x. We use z to approximate mu. And then, because we use z to approximate mu, in this case, what we need to do here is just to check the log z versus x1 to xk. So basically, originally we have the relationship of our assumption is log mu versus x1 to xk, and here we replace mu as z, replace mu with z, and in this case we just look at log z versus x1 to xk. So this is the idea, but in order to understand that why we can use z to approximate mu, I do not think that's easy. So I will give you one explanation, but it's a little bit beyond the scope of this course. So remember that what's Poisson count? Poisson count here is actually a very special case of binomial count. So what's the meaning? So that means we actually have the total number of trials n, but m is not observable and also m is very large. And this Poisson count is actually the number of the real events. So we should have this xzm for the in a standard data case. But here, because we have this Poisson count, so usually we do not have m. But we can still use this m idea to help us to understand it. So if we have m, we can actually predict, or not predict, we can actually estimate the probability of success by using z divided by m, if you still remember. So this is from the binomial logistic regression model. So you need to see topic 13, I think. And if we have the probability of success, so the next question here is that what is the mean of z? So we can use pi tilde here, which is the probability of success. So how to estimate the mean of count z? So by using the binomial idea, if you still remember, the mean of z mu is equal to the total number of trials m times the probability. So by plugging in the probability here, by plugging in the estimated probability here, we can obtain the estimated mean of z, so which is equal to m times z divided by m, which equals to z. So that means we can actually estimate mu by using z. And this part is we use binomial idea to understand Poisson count. So I think it's also beyond the scope of this course, but I can give you a slightly I think I can give you a very brief idea here to explain why we use z to approximate mu in this case. So what you need to do here in this course is just to remember that we use z to approximate mu, and what we need to do here is just to check log z versus x1 to xk. So I think it's, I just briefly mentioned it, so if you are interested, you can have a look, but if you are not interested, I think it's totally fine, just to remember the conclusion here. I think it's fine. So let's take 10 minutes break, and then we will continue this topic. So could you wait me there? So I will be downstairs very soon. Okay, let's start the second part of today's lecture. And so in the previous lecture, basically, we tried to answer the questions on the discussion forum to make the model diagnostics of the Poisson log linear regression model. And here, we propose to use this log response versus experimental variable plot to check the generalized linearity assumption. And in order to do that, the idea is from the assumption itself, because in the assumption, we assume log of mu is a function, linear function of experimental variable. So in order to check it, we need to find something to approximate mu. And here, by using this binomial idea to interpret the Poisson count, we can find that exactly we can use Z to approximate mu. So in this case, what we need to do here is that because the assumption says log mu has a linear relationship with the x1 to xk. So what we need to do here is just to check the relationship between log z and x1 to xk. And in this case, we obtain our log response versus experimental variable plot. So that's how we do that, even though the idea behind it requires the understanding of the relationship between the binomial distribution and the Poisson distribution, which may be beyond the scope of this course. And in this case, we try to draw this plot by using R. And also, if the assumption is true, we should have this straight line. Otherwise, we may have different cases. So in order to have to know how to solve this the problem if we do not have a straight line, so you may try to read topic 4, which is about I think it's about the response versus experimental variable plot for multiple linear regression. But the idea is very similar, so you can borrow some ideas from topic 4 to try to solve the problem. For instance, maybe we need to involve a quadratic term in the mean of response, maybe log mean of response. So in order to get the plot, firstly, we need to know that because Z is a count, is a binomial count, so Z can be equal to 0 in reality. So in this case, in order to avoid this kind of strange case, we need to add a small quantity to values of 0 if we really have that situation. And I think if you still remember this, it's really similar to the case for the binomial logistic regression model, because in binomial logistic regression model, we typically have the same situation. So in order to do that, firstly, we need to consider the 0 observations. So if the number of the accidents equal to 0, so we add a very small quantity, and here we add 0.5. Otherwise, we have the exact same value. So by using this if-else function, we can actually define a new number of accidents without any zeros. So basically, we only replace those 0 elements by using 0.5, very small quantity. And then we just plot the log of the number of the car accidents versus the number of lights. And this is our log response versus experimental variable plot. And the next step is just to have a look at it, whether or not it's a straight line. And here, in this plot, I do not think it's really straightforward. You can have a try. I do not think it's really straightforward that it's a straight line. So it's really hard to see for us. And also, I do not think we can clearly find a pattern in this plot. So could you find a pattern for this plot? So I'm really not sure about it. So in this case, I think if you can see a very clear pattern, for instance, a quadratic pattern or an increasing or or a very or a nonlinear pattern, curved pattern if the pattern is obvious, so you can propose to consider the other mean function. But in this specific case, because we cannot find very specific pattern, so in this case, maybe we just continue and try to use other diagnostic tools to help us to check all the other, all the assumptions. So in this case, let's just basically ignore it, because we cannot find a very clear pattern. So here we may have this conclusion that it's okay to use this linear function. And this case is really special, because it's really hard to find a pattern. And also, if we say it's linear, and I'm not that persuaded by that, but if we say it's not linear, we need to find some pattern to say it's not linear, but we cannot find a very good pattern to describe this kind of relationship. So my suggestion is just keep it here, and then look at the other methods to deal with the model diagnostics. And the second one here is the Pearson residual plot. And in order to define the Pearson residual, we need to review the student height residual. So something similar, I think, in the binomial logistic regression. So firstly, for the student height residual, it is for the multiple linear regression model. It's not for the generalized linear model, but the idea can be borrowed in the generalized linear model. And firstly, in the multiple linear regression model, we can have the fitted value, and the difference between the observation and the fitted value is the residual. So here we can obtain our residual. And for residual, we can obtain the standard deviation. And I have already mentioned it, but I will repeat it again. So sigma is from the constant variance assumption. Variance. And HI is actually the leverage. And the leverage is used to measure the distant explanatory variable values. And if you forget it, please review it. And in order to obtain the standard error, we need to replace sigma, because sigma is unknown, with the sigma hat. And sigma hat is the estimation of sigma. And in this case, we can standardize the residual by dividing the standard error of the residual, such that we can view all the residual on the same scale. And if we have this case, we can call it a student height residual. And the good property for the student height residual here is that if all the assumptions are satisfied, then in this case, the student height residual should be roughly standard normal distributed. So that's the review from the multiple linear regression model. And let's just look at the Pearson residual, so which is using the similar idea, but we consider the count response. So we also have the fitted value, if you still remember. So that I had is actually the fitted value. So how to obtain the fitted value? So Z hat fitted value equals to estimated of mean of response y given x, and which is the exponential of the beta 0 hat, beta 1 hat, x1 plus so on and so forth, plus beta k, xk. So that's the fitted value. So given each value of x, we can obtain a fitted value. And if we compute the fitted value and the difference between the observed value and also the fitted value, we can obtain residual. And the next step is just to obtain the standard deviation. So here I just give you the standard deviation directly. So the standard deviation here is the square root of mu I. So what's mu I? So I think we need to clearly specify this. So let's just try to write down the mean fitted value given each I, xi, and the mu I is actually the exponential of beta 0, which is the true value but unknown, beta 1 x1 I plus so on and so forth until beta k x k I, which is the ith mean of response, which is the ith mean of response, so maybe I just write it as the mean of zi. So why we have this result? So this is actually from zi follows the Poisson distribution with the parameter mu I. It's actually the Poisson distribution assumption. And if we have this result, we can compute, if you still remember, the mean of zi, here equals to mu I, if we have this result. So how to compute the mean? I have already mentioned it, I think, earlier. So how to compute the mean? It's from the how to compute the mean of the discrete random variable. Here. So you can do it to compute the mean of the discrete random variable. And then you will find that the mean is exactly the mu, which is our which is the parameter in the Poisson distribution. So the mean of zi equals to mu. And another property for the Poisson distribution here is that the variance of zi also equal to mu. So how to compute the variance? So if we can compute the mean, we can also compute the variance. It's also something, I think, in the STAT 1008 and STAT 7055. So I think similarly to the computation of mean, you can compute the variance. And you can find that for Poisson distribution, the mean equals to the variance. I think this is the only distribution we have that mean equals to variance. And because the mean equals to variance, so the standard deviation of zi just equals to the square root of mu I. And here, similarly, we can have this result. The standard deviation of the residual here is also mu I. And because mu I is unknown, because in the mu I we have the unknown beta, so what we can do here is just to replace those beta with the estimated beta, and then we can obtain the standard error. The standard error just equals to the square root of the zi hat, and zi hat here is actually the estimate of mu I. And then we can define the Pearson residual, and the Pearson residual is a residual basically divided by its standard error. So we consider the standardization, and in this case, we can treat Pearson residual on the same scale. And if the assumption is satisfied, so we should have the Pearson residual roughly standard normal distributed. And in this case, we should have we can use this normal distribution to help us to identify whether Ni is from the Poisson log linear regression model. And here, there is something I need to tell you, is from this derivation of the variance of Zi, we can find that variance is different for different I. So that means no constant variance for Poisson log linear regression model. So because I think here we only have 3 assumptions instead of the 4 assumptions in multiple linear regression model. For Poisson log linear regression model, we only have 3 assumptions. And by using the first 2 assumptions, by using the Poisson distribution assumption and also the generalized linearity assumption, we can derive the variance of response zi equals to mu I. And we find that the variance is different for different I. So in this case, we do not have the constant variance assumption by using the 2 assumptions of Poisson distribution. So I think this result is based on Poisson distribution assumption and generalized linear assumption. So by using these 2 assumptions, we can definitely obtain that we do not have the constant variance assumption. So in this case, we cannot add this constant variance assumption for the Poisson log linear regression model, because from the model we never have this kind of situation. We always have non-constant variance assumption, non-constant variance case based on the first 2 assumptions in the Poisson log linear regression model. And I think similarly, if you still remember the binary logistic regression model, so this is topic 10. In binary logistic regression model, we also look at the variance, if you still remember, the variance of response. They are also not different. They are also different. So in this case, basically for all the generalized linear model we have mentioned in this course, so the conclusion is that for all the generalized linear model, we never have constant variance. Because we never have constant variance, we do not need to check this assumption. So that's the reason why if you review all the generalized linear models, you will find that we always have 3 assumptions. The first assumption is to specify the distribution. The second assumption is to specify the generalized linearity. And the third assumption is to specify the independence. So remember that in generalized linear model, we never talk about constant variance because we do not have this property at all. And let's just go back to this Pearson residual. So in this case, because we have the Pearson residual on the same scale, so we can use this normal distribution to help us to check whether or not one observation is an outlier. So here, this Pearson residual plot is to check whether some observation I, so basically it is used to check some observations, satisfies all the conditions, all the assumptions actually, in Poisson model. So that means it's used to check all the assumptions, but only for some observation I. So that means we can only check whether or not some observation I satisfies all the assumptions. And you can have a look if the Pearson residual is larger than the 97.5% quantile or smaller than 2.5% quantile of the standard normal distribution. In that case, this Pearson residual falls into 2 tails of the normal distribution. But if we consider the normal distribution concentrate in the middle. So in this case, those i's is an outlier. So that means those i's possibly those i's are possibly, I think not, those i's possibly not satisfy the model assumptions. So what's the meaning here? So that means those i's may not satisfy the, for instance, the Poisson distribution assumption, or the linearity assumption, or the independence assumption. So it's all possible in this case, but we do not know which one it is. So that's the meaning for the outlier. And how can we do that? We can use this Pearson residuals function, but we need to specify Pearson here to obtain the Pearson residuals, and then we can plot the Pearson residuals. And cutoff here is 1.96 and minus 1.96. We can use these two red lines to represent these two cutoffs. And we can find that here we have number 24. You can look at it. And also we can have this maybe number 26 or something. So we have some outliers. So that means those assumptions may not satisfy the Poisson log linear regression assumptions. So that's how we use this Pearson residual plot to check whether or not some observations satisfy the assumptions in Poisson model. And this is about the Pearson residual. And then let's just try to answer the question from the student. So the student used a slightly different way to check those assumptions. So firstly, we have our Poisson log linear regression model. So let's just look at firstly look at the Pearson residual plot. So this is the plot. And by using this plot, we can actually obtain, so which are outliers. We can obtain this kind of conclusion. But the students suggest us to use the plot, the GRM output, which is here. And the next argument is which equals to 1, right? And where is the, okay, I think I have closed the plot. Here. So this is the plot by using the command suggested by the student. And in this case, it's slightly different. And firstly, we have these residuals instead of the Pearson residuals, right? And secondly, it's actually residuals versus fitted value plot. So what's the fitted value? So the fitted value I have already mentioned basically is the estimated mean of response in the log linear regression model. So it's actually something similar compared to the multiple linear regression model, but we haven't talked about it in the generalized linear model. But you can actually do that. You can still do that, I think, in the generalized linear model. It's not a problem. And also, you can use the standard in the multiple linear regression model case to understand this plot, because basically the meaning is very similar. It also means residual versus the predicted value or versus the fitted value plot. So if we cannot find a pattern in this plot, so here we have a slight, maybe we have a pattern, a little bit curved pattern here. But I think this pattern is not that, I think it's really vague compared to the baseline. So the baseline is 0. So in this case, we can see that because basically most of the points are around the zero horizontal line. So in this case, and also it's really hard to find a pattern, even if we have this very small pattern here. So we can see that I think it's fine to consider to use our model. So that means the Poisson model, including the linearity assumption and also Poisson distribution assumptions, I think they are fine. But this plot is not introduced in our lectures, so that means it's not required in this course. So my suggestion here is that sometimes even we can use residuals, and also we can obtain some outliers. For instance, we still obtain 24 here. And if you compare this 24 to the one, I think, in our lecture notes, we also have 24. So we can have the very similar conclusions. But my suggestion here for the generalized linear model, I think maybe it's easier for us to use the Pearson residual because it's much easier to understand, because we can look at those on the same scale. So my suggestion here is that maybe we not use this which function. And the reason here is that not use this plot which function suggested by the student, because the reason here is that it's actually not that clear by use this function in this course, because we haven't mentioned about it. But in the lecture notes, we have clearly pointed out the meaning for the Pearson residuals. So using Pearson residuals to identify the outliers, I think it's more straightforward. I think that's just my suggestion. But we can actually use this which function, which we haven't talked about it. We haven't talked about, but you can use it. So that's the answer. And I think in the lecture notes, I think I basically focus on because it's just an introductory level course, I only focus on very straightforward and also basic diagnostic tools instead of the function generated by which. So I do not talk about the plot which function, I think, in this course, so maybe I can write. So we don't talk about plot which function for diagnostics in this course. But you can use it. The problem here is that in order to explain that plot, you need to understand the more details behind the plot in order to understand why we consider to use those plots to help us to perform the diagnostics. So I think in this course, because it's an introductory level course, so we only use very simple tools. The first tool is the log response versus explanatory variable plot. Even though it's simple, but I still need to spend a lot of time in explaining the meaning of this plot. And the second one is this Pearson residual plot, and I think it's very similar. So in order to firstly, we use this plot to check whether or not some observations whether or not some some observations satisfy the model assumptions. And also, if we have a look at this plot, and also if we find that around 0, we cannot find a pattern for most of the points. So you can see that for most of points, we cannot find a pattern. So that can imply most points or most observations satisfy the model assumptions. And here, this model assumption means all 3 assumptions. So that means we can actually use this Pearson residual plot to check all 3 assumptions. The reason why we can use it is that because we get this conclusion, roughly standard normal distribution here is actually from all 3 assumptions. Remember that firstly, we have the linearity assumption, generalized linearity assumption here to compute the estimated mean of response, and then we compute the residual. So that means the generalized linearity assumption is involved in deriving this Pearson residual. And secondly, we use the variance of Z, which is equal to mu I, to derive the standard deviation and also the standard residual of the standard error of the residual. So in this case, the Poisson distribution assumption is involved in the standard error part. So you can consider in this way. So the residual can be represented by using the generalized linear assumption. And the standard error is actually from the Poisson distribution assumption. Because when we construct this Pearson residual, we use both assumptions. So in this case, we actually, if this Pearson residual is really normal distributed, we should have these 2 assumptions satisfied. And also because we consider a lot of residuals, and when we look at this pattern, we try to find a pattern, and here we cannot find a pattern. So in this case, to some extent, we also check the independence assumption, which I think is not emphasized in this course, the independence assumption. So I think we do not focus on checking independence assumption in this course. So basically, we haven't mentioned anything about checking independence assumption. But what we can tell here is that if we do not have a pattern in this course, in this plot, but if we don't have a pattern, usually independence is okay. So I think in other courses, for instance, you may have some pattern here in this plot, because here we actually plot the Pearson residual versus the index. So that means for the x-axis, it's actually the number of observations. So if there is some pattern, I think in some course, especially when we have the time series index. So that means we actually have the time series observations. So if we have some kind of pattern, so that means we actually have the time dependence. But I think the problem here is that we do not usually have the time series observations in this course. So usually in this course, we just ignore it. And also, another problem here is that the dependence is not limited to the time series dependence, and also we have the spatial dependence, we have the network dependence. It's actually, in order to talk about independence, basically in this course, it's not possible. Even though I'm working on it, that's my research. So my idea here for this course here is that just ignore the checking the independence assumption. So that's my suggestion. But if you are interested in studying the time dependence, you can enroll in my course next semester, Applied Time Series. But if you are interested in other kind of dependence, for instance, spatial dependence and also network dependence, you may just maybe figure out it by yourself, or you can, if you are interested, you can chat with me during my consultation hours. But in this course, we do not emphasize to check the independence assumption in this course because dependence is too complicated. So if you are interested in checking time series dependence, you can consider apply time series analysis. So in conclusion, by using this plot, we can do two things. The first thing here is just to check whether or not some observations are outliers. And the second thing is just to check whether or not most of the points satisfy all three conditions. So that's the Pearson residual plot. So we have, I think, even though it's really similar to the binomial logistic regression model, but I think I explain it, I think, in deep explanations. So in this case, I think maybe you still need time to process it, but if you can, just to try to understand the idea, but if you cannot, just try to understand what we can use those diagnostic tools for. So the last one is the deviance goodness of fit test. So I have already mentioned it in the binomial logistic regression model. And also in the beginning of the previous lecture, I also compare it to the dropping deviance test, if you still remember the deviance. So here, that's the difference. So the difference here is that the deviance goodness of fit test is used to test whether or not the model assumptions hold, but the dropping deviance test is to test several coefficients under the assumption that all the model assumptions are satisfied. So if we do not have the model assumptions are satisfied, we can never use the dropping deviance test. So firstly, we need to use the deviance goodness of fit test to test the model assumptions. And what I can tell you here is that in this deviance goodness of fit test, even though we only write down the generalized linearity assumption, so this is the generalized linearity assumption, but we actually, so it's not that accurate, we actually need to add, because for model Poisson, log linear regression model, we actually have three assumptions, the first, the second, and also the third. The first assumption here is the Poisson distribution. Poisson distribution assumption. The second is the generalized linearity assumption. And the third one is the independence assumption. So by using this deviance goodness of fit test, we are actually testing this whether or not these three conditions hold. Not only the linearity assumption. But for simplicity, usually we just write down the generalized linearity assumption here as our modeling. So that's only for simplicity. But you need to know that here we actually test these three assumptions at the same time. And the test statistic is the deviance of the model. And if these three assumptions satisfied, we can find that this test statistic can be approximately this chi-square distribution. So this chi-square distribution is exactly from these three assumptions. So we use these three assumptions to obtain this chi-square distribution. And if we do not have these three assumptions, we can never use this chi-square distribution as the comparison. And here I need to talk about what's m, what's k, and what's 1. I think k is obvious because k it just means the number of the explanatory variables. So what's m? So the meaning for m here is exactly the same as the m in the binomial logistic regression model. So it's actually from our beginning. So how many observations we have in this case? We have 41 because we have 41 counties. So m equals to 41. So you need to know this m just equals to the number of the observations. And then we can use this test to obtain the p-value, and this is how we compute the p-value. But usually in R, we can only compute the probability that a random variable is smaller or equal to some value. So if you still remember the Poisson probability case, we can obtain this smaller or equal to probability. So what we can do here is just to use R to accomplish this. And what you can do here, firstly, is to use the summary output to obtain this summary result. And in this summary result, you need to call the deviance. So if you use this summary result deviance, you will obtain the model deviance. So this is the residual deviance, and it is the deviance of the model. So here, our model here is log mu z given x equals to beta 0 plus beta 1 x, and x is the number of the traffic lights. So you can use this deviance to obtain the, the deviance of the model. And also you can use this degree of freedom to obtain the degree of freedom of this test, which is m minus k minus 1. So here, m equals to 41, and k equals to number of the variables, which is 1, and then we have 1. So 41 minus 1 equals to 39. And also you can find this 39 here. So this is the degree of freedom. And by using this, you can use this p chi-square distribution to obtain the probability. So you can use this function to obtain the probability that a chi-square distribution, so maybe I should write that the S follows the chi-square distribution with m minus k minus 1 equals to chi-square distribution with the number of degree of freedom 39. So the chi-square distribution here, which is smaller than the number of the smaller than the test statistic, which is the deviance, and here is 51.011. And what you can do here is just to input this 51.01 here and put the number of the degree of freedom here. And then you can compute this smaller or equal to probability. But the p-value is to compute the larger or equal to probability. So in this case, this whole command line returns the probability that chi-square distribution of 39 is larger than 51.01163. So that's the p-value. And you can see that this p-value is larger than 0.05. So at this significance level, we do not have any evidence that this model is inappropriate. So that means we cannot reject the null hypothesis. But if we consider at the level 0.10, we reject. So that totally depends on you. So you need to select the significance level by yourself. But this, so at the level 0.05, we cannot reject, but at level 0.1, we reject. This kind of very vague conclusion also confirms the result, if you still remember, in here. So in this plot, we can really, it's really hard for us to determine whether or not the assumptions are satisfied, right? And also, if we look at the test result, we also have very vague cannot reject result here. But